Hello, I'm Andy Peel from the CCDC and welcome to this video on glide symmetry. In this video we will look at the definition of glide reflections and of the associated symmetry elements glide planes. After watching this video you will understand the meaning of a glide reflection and glide plane, be able to identify molecules related by simple glide reflections, and be able to identify simple glide planes from a unit cell and its contents. We will use examples of molecules and structures taken from the Cambridge Structural Database, or CSD for short, to illustrate the concepts involved in glide symmetry. To begin with, let's give some definitions. A glide reflection is a symmetry operation consisting of a reflection through a plane coupled with a translation parallel to this plane. A glide plane is a symmetry element associated with a glide reflection. Geometrically, this is just a plane. The symmetry operation is what we have to do to get from an object to its image. In this case, the object is a molecule, and the plane tells us where we need to reflect the object. The plane is a fairly easy thing to draw on a crystal structure, and we have simple rules that tell us about the translation part. Glide reflections are similar to regular reflections in that a mirror image of the object is created by the symmetry operation. This means that a chiral object changes its handedness during a glide reflection, which would be analogous to creating the enantiomer of a chiral molecule. Looking at these diagrams, we can see that the difference between regular reflections and glide reflections is the translation of the image from the original object, in this case the enantiomer of the original chiral molecule. In the animation, you can see what happens if we keep on applying a glide operation. A line of molecules is created in a zigzag pattern, with the second, fourth, and so on molecules being enantiomers of the first. Of course, real crystals are not just a line of molecules, and in 3D there are a number of possible glide reflections which we can describe by the position of the plane and a direction and distance for the translation. These features are referenced to the unit cell of the structure and must obey other symmetry requirements of the structure. It turns out that just considering the periodicity of a crystal, the translation part of the glide reflection has to be parallel to certain directions with respect to the unit cell. This is because applying a glide reflection twice must get the molecule back onto an equivalent position in the next unit cell. The simplest case would be a translation parallel to one of the unit cell axes. In the first example, this is a translation parallel to C with length a half c. This is called a C glide. If it were parallel to A, it would be called an A glide, and so on. The second example involves a translation parallel to a face diagonal of the unit cell, which consists of movement a half along A and a half along C. This is called an N glide. To make things easier, we can use colours to help identify molecules. The magenta molecules are related by a glide reflection to the original molecules, which are coloured silver. Returning to the example of the molecules in a line, we can mark on reference points for the original molecules and glide reflected molecules. It then becomes obvious that the repeat length here is twice the glide translation. Now it's time to see an example. Malic acid, which has CSD ref code MALIAC13, has a monoclinic structure, and the only symmetry in the crystal is a C glide perpendicular to B. What this means is that the molecule is translated by a half C and then reflected in a plane which is parallel to the AC face of the unit cell. In the animation, the plane shown is at y equals a half. It turns out that the symmetry of the crystal requires such planes to be at y equals 0 and y equals a half with respect to the unit cell. Let's return to the first molecule we saw and view it together with the unit cell of the structure. Can you identify from the projections along the A, B and C directions that follow what type of glide reflection is present here? Where are the glide planes located with respect to the unit cell axes? Look for the same functional groups in each molecule and see how they are related by translation and reflection. Try to express these as distances, directions, and positions in the unit cell. Pause the video on each of the following 3 projections to study them in more detail. Let's look through those. In the projection down the A direction, we can see that the molecules are reflected, for example look at the phenol groups, in a plane which contains C and is perpendicular to B. It cuts the y-axis at a half. You can also see there is a translation by a half C. At this point, it's possible that this is a C glide. Now look at the projection down C. Here, there is a reflection across a plane that is perpendicular to B and contains A. You might also spot that the displacement of a molecule and its reflection is a half A. So far then, we can say that there is a glide plane which contains the A and C directions perpendicular to B at a height y equals a half, and that there is a translation along the C direction and the A direction. The translation is by a half C and a half A, so we have an N glide rather than a C glide. We can confirm this by looking at the view down B. As you can see, the translation is parallel to the face diagonal in this projection. Like in malic acid, considering the periodicity and symmetry of the crystal, there must also be a glide plane at y equals 0 as well as at y equals a half, and that repeats throughout the structure. To summarise, in this video we have learned about the glide reflection symmetry operation and the glide plane symmetry element. You have seen 2 examples, an axial glide and a diagonal glide, in small molecule crystal structures, and have used the unit cell as a reference to identify the type of glide relationships between molecules. We hope that you have enjoyed this video and that you found it useful for learning about glide symmetry. You can explore symmetry in crystal structures further by using the symmetry display feature which is available in free Mercury. Give this a try with CSD entry CEJLOS. Find out more about glide symmetry and how to view symmetry in Mercury from the resources linked in the description. Thanks for watching, and don't forget to subscribe to our YouTube channel.